Hello dear students, hope you're doing well. So today we have chapter 2. First, let's talk about experiments and generalizations. We already took generalizations back in grade 9, I think. So first, what is an experiment? Let's define it. Experiments, there are controlled sequences of observations, things you observe but in controlled conditions. For example, let's say controlled temperatures, constant temperatures, pressures, and other factors. You control them. So we have something controlled and we have something variable that changes. Then you take notes, you take data from the experiment. Then your experiment will lead up into having facts in science. So facts and science, things that we know right now, all of them are due to past experiments that scientists have done. Generalization is a general observation or something you observe based on only number of experiments, not that much. So it's a general rule framed on a collection of individual facts. Okay, so when is a generalization applicable? You can apply it on something. It is within the bounds defined by the experiments that led to this route. So you connected to the experiment itself, then it will be applicable. In science, we make observations. Things we see, we observe. Then we generalize. We say what you think about that observation. It might not be true, it might be true, it might not be true, it might be not 100% true, it depends. So it is this generalization, it is retained as long as it constitutes with the known facts, as long as it agrees with the known facts. Once it disagrees with it, even for once, then you have to modify your generalization because it has been falsified. So exercise number 1, what is an experiment or define experiment? Experiment is a controlled sequence of observations. Question number 2, what is a generalization? Define it. Generalization is a general rule framed on a collection of individual facts. When is it applicable? A generalization is applicable within the bounds that are defined by the experiment that leads to the rule. Question number 3, when is a generalization retained and when it should be modified or dropped altogether? It is retained as long as it constitutes with the known facts. So it is kept alone. You change it or you modify it when once it disagrees with the new facts, it should be modified or even dropped altogether. It depends. If you can change it, you change it. If not, you have to drop it altogether and, for example, make another generalization based on known facts. Chapter 2, section 2 will talk about changes of state. First, we have to know how many states we have. You know that we have solid, liquid, and gas. We have the first state, but we do not talk about it. It's too complicated for you. So changing from, for example, let's say solid to liquid or liquid to gas, gas to liquid, liquid to solid, or even solid to gas or gas to solid, we call them changes of state. Let's take an example. If you want to change from a solid into liquid, you know that solids, their atoms are close to each other, packed together. Liquids, they are a bit away from each other. So in order for this to happen, you have to heat it. You have to increase the temperature in order for them to have enough energy for particles to separate away from each other into having this much distance between them into becoming liquid. The temperature at which this happens, we call it melting point. Let's take a look at the shape of the graph. The heating curve, we call it the heating curve when we change from solid to liquid or liquid to gas. But the exact opposite, we call it cooling curve, changing from a gas to liquid, liquid to solid. Okay, so this is the heating curve. So it's in between. We have the y-axis, which is temperature, and we have the x-axis, which is time, how much time it spends. And we have a certain point when the curve becomes straight line, that is your melting point. Okay, so you start from here, from the origin, you go up, this up until you get to the straight line. All of this, we only have the solid state. So solid starts to melt. At this point, at melting point, we have both of them. So we have solid and solid starts to melt. So we have both liquids and solids. For water, the melting point is 0, but not for all substances. Each substance has their own melting point. So above this melting point, if you go above 0, even 0.1, everything will become liquid. Okay, so we start with solid. In the middle, when we have a straight line, when we have the melting point, we have both of them, solid and liquid. When you go up, we only have liquid. So look, it's a heating curve. It goes up because energy is absorbed, because temperature rises. Okay, but for cooling curve, we'll talk about it later. It goes down because you're lowering the temperature, so low heat. If, let's say, we compare two substances, two samples with different masses, let's say a small ice cube and a big ice cube. Okay, so if I ask you which one of them will start to melt at 0 Celsius, or which one of them has a melting point of 0 Celsius, you should say that both of them start at 0 Celsius. Okay, it does not depend on how much it is or how big it is. Both of them start at 0 Celsius. Why? Because both of them are made up of water. But if I say which one of them will take more time, you will say the big one. Okay, this is the difference between them. But melting point, it is constant. It's a physical change, so it is constant. It does not change. Look at the differences between them. We have I, the small ice cube, let's say. The big one is double I. Okay, look at it. Both of them, the straight line is at this point. Okay, so both of them have the same melting point. But look at the time. When this is time, which one of them took more time? So let's talk about I. How much time did it take? It started from here up until here. Okay, this is how much time it took. For double I, it started from here up until here. So look, this is for double I. So it took more time. But again, both of them have the same melting point. So the straight line, both of them will be the same thing. So we have some things to consider. Depending on our experiment, we have some observations that A, the two samples will have the same melting point, do not forget. B, the larger sample will take more time, longer time to start to melt, and it will take a longer time to melt completely. Let's go to basic question. The following is a warming behavior of 1 gram of a pure substance. We do not know what this substance is. What is the melting point of the substance? Where is it? Look, straight line, go, 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 go. This is your melting point. So it's basically, let's say, approximately 32 Celsius. When does the compound start to melt? Look, at point B. Okay, so point B, at 30 seconds, it starts to melt. How long does it take, the melting process? You started from B up until C. You have two numbers, subtract them. You will know how many seconds does it take. D, in which state does pure substance X exist between A and B? Which state is it? Look, it's a warming behavior, meaning we are starting with solid, going to change it to liquid. In between them, we have both of them. So at this point between A and B, this point, we only have solid. At melting point, we have solid and liquid. Above melting point, we have only liquid. Let's go to the cooling behavior or cooling curve of pure substance. For heating curve, we increase the temperature. For cooling curve, we decrease the temperature in order for it to be cooled down to change the state. For example, let's say we change liquid to solid. You put it in the freezer, right? So you have low temperature or decrease the temperature. So instead of our curve to be something like this going up, it will come down. Okay, and here for heating curve we had melting point, right? For cooling curve we have freezing point. This is it. This is your graph. So you have temperature again and time again. What do we have? The straight line. It's a cooling curve, meaning we have freezing point. Look at the freezing point. For water it's still 0 Celsius. So for any substance, pure substances, melting point is equal to freezing point. So for water, let's say it's 0 Celsius melting point, the freezing point should also be 0 Celsius. For another substance is 30, the freezing point should also be 30. Okay, same concept. So here, because it's freezing, you start with liquid, you change it to solid. So what do you have at the beginning? Only liquid here. Here at the freezing point, you have liquid and solid, and at the end we only have solid. Same concept you can apply it on the cooling curve. If you have two substances, let's say 2 liters of water and 1 liter of water, which one of them is bigger? The 2 liter is bigger than 1 liter. So let's say we have I and we have double I. Which one of them will take more time for it to freeze? The bigger one will take more time. But which one of them will freeze at 0 Celsius? Both of them, because both of them have the same substance, both of them are water. So look, how much time did I take, the small one from here to here, the big one from here up to here. But both of them are at the same freezing. We have an experiment 2.1. It does not need a lot of explanation because at school you do not have the apparatus to do the actual experiment. But just read it once. Do not memorize anything, especially the procedure. No one memorizes it. Even chemists, they just follow it. It's a paper, they just follow it step by step and do it. So in general, this experiment is about how to calculate or how to find out the melting point of a pure substance. Just read the steps and that's it. It's not that important, and most of the time in the exam questions do not come from experiments. If you do want to know something about the experiments, just read the questions on the experiment. Read them and get the answers from the end of your book. So 2.3, we have a generalization about melting of solids. What does that mean? Melting, when a solid changes into liquid, that's melting. The exact opposite, when a liquid changes into solid, that's freezing. What about solid changing into gas? We call it sublimation. The exact opposite, gas to solid, is deposition. Okay, so here from solid to liquid, the point at which this happens, we call it melting point. For freezing, we call it freezing point. For liquid, when it changes into gas, directly into gas, that's evaporation. The exact opposite, gas into liquid, that's condensation. These are constant, meaning such as boiling point, density, index of refraction, melting point, freezing point. All of these are called physical constants. We already talked about these. They are constant. It means that they do not change. They do not depend on how much matter is inside an object, how much is the size of an object. If it is made up of the same material, it will have the same physical constants. They do not change, such as melting point for water, for ice, it's 0 Celsius. Whether we have a small cube or we have a large cube, it's still 0 Celsius. Okay, let's go to basic question 3. A substance changes from solid into liquid. What do we call it? Melting. The second one, it changes from liquid to gas, that's evaporation or boiling. C, it changes from liquid to solid, freezing. D, changing from solid directly to gas, that's sublimation. E, changing from gas to liquid, that's condensation. Next, we have the difference between states and phases. What do you mean by states, or what is the difference between states and phases? So states, we already talked about states. We have solid, liquid, gas. Phase, how many uniform mediums do we have? Meaning when you look at something, how many layers, specifically, how many layers do you see? That's how many phases you have. For example, if you have water and oil, they do not mix, right? So you will have two layers. We will have oil at top, water beneath. Because we have two layers, that's two phases. But if we talk about states, how many states do we have? It's just one, because both of them are liquid. So oil is liquid, water is liquid, so only liquid state. Both of them are in liquid state. But for example, let's say if we have ice in water, okay, how many phases do we have and how many states do we have? Let's talk about states. States, we have ice, which is solid, in water, which is liquid. So how many states? Two states. What about phases? Will we have two layers or more than two layers? Yes, because the ice cube will float at top and we will have water beneath it. So how many phases? Two phases. Okay. Let's take some examples. Basic question 4. Fill in the table with the correct number of states and phases. Let's say we have alcohol and water. When you mix them, know something that when you mix alcohol and water, they dissolve into each other. Okay, so how many states do we have? Both of them are liquid, so only one state. Both of them, because they dissolve into each other, they mix, meaning we will have only one phase. The second one, alcohol and sugar. Alcohol dissolves sugar. Know this. It does not dissolve salt, it only dissolves sugar. So how many states after mixing? How many states should we have? Will we have only one, which is the solution. How many phases? How many layers? Only one layer. If we have oil, water, and chalk, how many states will we have? This is liquid. This is also liquid. Will chalk dissolve in water? No, it's a solid. How many states do we have? Solid and liquid, so two states. How many phases do we have? We will have three phases. Why? Because let's say we have a glass of water. We'll have water here, oil above it, and bits of chalk suspended in the liquid. So you'll have three different phases. The last one, we have salt, water, and sand. Salt dissolves in water. This is solid. This is liquid. Sand is also solid. So how many states? Two, solid and liquid. How many phases will we have? Because salt dissolves in water, that's one layer. The other layer, which will be at the bottom of the flask, sand. So how many layers? Two. How many phases? Chapter 2, Section 4. Scientific models and uncertainty in science. First, let's talk about models, or to be specific, scientific models. What do they mean? And we will have some examples about them. Scientific model is something that gives an explanation of something we do not understand by comparing it to something we do understand. For example, a map, it tells us or it shows us how the world is. If you flatten it out, meaning how countries are beside each other, the continents, the ocean, and everything on Earth, it is shown on this map. And we have a lot other examples. Scientific models, it should be simple, it should predict the future. But something you have to know about models is that they're not an exact picture of what is happening, just an explanation, a useful explanation to let us understand something. Let's take an example. For example, we have a balloon. If you fill it with air, it will be bigger, right? So the size will become bigger. Why? Because we have gas molecules And something about gases is that they constantly move, so they hit each other and they hit the walls of the container. That's why the container or the balloon becomes bigger when you fill it with air. More air goes inside. Can we, let's say, explain the characteristics or the properties of gases by using billboard? Yes and no at the same time. We have the model of gases. As we said, they constantly move, so they hit each other and they hit the walls of the container that they're in, depending on where they are located. For example, a balloon, let's say, gas particles hitting each other and the walls of the container. That's why it's hard and that's why it expands. Can we consider a balloon filling it with gas a good model to be used to explain properties of gases? Yes, it can be used, but can we, let's say, the billiard game, can we use it as a good model to explain properties of gases? No. Let me give you one reason. One of the reasons is that when the billiard balls they hit each other, there will be point in which they will stop, right? But gases, when they move, they never stop. They constantly move, they constantly hit each other and the walls of the container, they do not stop. So that's why we cannot consider the billiard as one of the examples of explaining properties of gases or one of the models of talking about gases. But filling in a balloon with gas or with air, it is a good model. Another thing about gases, about particles of gases, other than they constantly move, they have constant kinetic energy. What do you mean by kinetic energy? Kinetic energy is the energy that particles have when they move. So moving particles, they have something, we call it the kinetic energy. Okay, something that does not move, it's constant, it's not moving, it has potential energy. Okay, so here for gases we will be talking about kinetic energy, in which it is constant, it does not give it out, let's say, or the total kinetic energy of the whole container, of the whole balloon, let's say, including all the gases, it should be constant. Even though when particles they hit each other, so particle number 1 hits particle number 2, this one, number 1, will give its energy to number 2. Then number 2 will have energy, it will hit another one, and so on. But the total should be constant, it does not change. But for the billiard balls, it does not. It gives it out as sound, as heat, and so on. So that's another reason in which we do not use it as a model, good model. So see, the thing that about models, and it is that they should explain or the possible explanations about the thing that you're talking about and even predicting what will happen in the future. So having constant kinetic energy for gases, particles of gases, we say that they undergo perfectly elastic collisions, in which that means there is no net loss of kinetic energy. They will have the same amount before and after colliding with each other. We said that the billiard balls or this model, we cannot use it as a good model to explain properties of gases, right? Then what should we do? So scientists, when they try to explain something by using a model and it does not work, they try to modify it. They try to make it better. If not, they just let it go and start another model in which that should be useful for it to explain all the things that they want. So models, they are said to be useful, but they can never be absolutely true or being proven to be correct. Only true so far. 2.43, we have uncertainty in science. All the measurements that we make or the scientists make, there is always a bit of uncertainty with it. If you remember in grade 8, we took uncertainty as being positive, negative, something, a number. Let's say 0.5 centimeters. If you want to measure, let's say, a length of something by a ruler, for example. What does this mean? The length that we get the answer could be more than this answer by 0.5 centimeters or less than this answer by 0.5 centimeters. This is your uncertainty. So every scientific statement involves some uncertainty, and therefore no scientific measurement is absolutely certain. That's why we say it's only true so far. It's not 100% certain. Nothing is 100% certain. And that's why when scientists get their results, they say within experimental errors. So explaining that they do not have perfect results. Even if they do not say that, you should know that is within experimental errors or within the uncertainty. Or let's say positive, negative, something, a number. Okay. The pressure and volume behavior of gases. What's the relationship between pressure and volume? Let's say we have a container, okay, filled with gas, only gases. When we talk about pressure, we are talking about gases because pressure does not affect liquids and solids. You cannot change their shape, you cannot change their volume by increasing the pressure or decreasing the pressure. The only thing or only state that can get affected is a gas. So we have this gas inside this container. You put pressure on it. You put pressure, meaning you're pushing it down. So what will happen to, this is the volume. What will happen to this volume? It will become smaller. So if you increase pressure, what will happen to volume? It will decrease. Okay? So there is an inverse relationship between pressure and volume. If you increase this, this will be decreased. If you decrease this will be increased. And these are some of the calculations. And it tells you to, let's say, sketch a graph of pressure versus volume and see what will happen to it. Drive the mathematical formula that summarizes it. And collect the equality with a number. So P times V, how much is it? It should be the same throughout the whole measurement, meaning if you multiply this should be a number, this a number, this a number, which is, I think, 22.4. That's the constant. The above, the relationship between pressure and volume, it has proven to be a law. We call it Boyle's law. Okay? So Boyle's law is the relationship between pressure and volume, which should be equal to a constant. So P multiplied by a V should be a number, should be a constant. Why? Because they have inverse relationship between them. Let's go to basic question, which is very important. How to complete this table. So look, we have V, we have P, and we have PV, so P times V. So we have, in the first one, we have 3 experiments. The first one, we have V, we have P. How much is PV? Just multiply it. So 6 times 0.7, which is 4.2. Okay, so look, we said that PV or P times V should be the same throughout the whole experiment. So if this is, even if you do not calculate the first one, if this is 4.2, so this should be 4.2 and this should be on 4.2 as well, without even calculating. Okay, the third one, so it's done. The first one is done. The second one, how would you calculate this? Look, we have V, it's unknown. We have P 0.4. We have P times V 4.2. So if P times V is equal to 4.2, what do you want? Volume. So volume is equal to 4.2 divided by pressure. So 4.2 divided by 0.4, which is 10.5. So here, 10.5. Same thing goes to the third one. We have V and we have P. So multiply them to get this. So if you want to get PV, just multiply your two numbers, you get PV. If you want to get one of them, either P or V, you should have PV and do this. Okay? Calculate one of them. If, let's say, here you want P, you will say P is equal to 4.2 or the constant divided by V. How much is V divided? You get an answer. This comes a lot in the exam. The last thing we have is testing our model of gases. So is it correct that if you increase the temperature, increase the pressure, volume will be decreased? If let's say we have this container, you put pressure on it, okay? So as we said, it only affects gases. Why? Because gases are free, they constantly move and there is space between them. So we can decrease the space. How? By increasing the pressure. So pressure is increased. What will happen to the volume? It will be decreased. Same thing goes if I say, if you have this container, I decrease the volume, let's say to half, okay? So half of this, you change it into half, volume is decreased. Well, what will happen to pressure? Look, we decreased volume, so this should increase. We halved this, so this should double. Just switch it. So 1/2 will be 2/1. This is a relationship between them. So yes, there is an inverse relationship between them. If let's say volume is halved, so decreased, halved meaning decreased, or if you have a fraction meaning you're decreasing it, what will happen to pressure? So 1/2 becomes 2/1. So it will be doubled. The last thing we have for this chapter, I want to show you the difference between these two heating curves. Same thing applies on cooling curves. For example, if we have this heating curve, we already talked about this. Heating meaning you're changing from solid, right, into liquid. So at the beginning we only have solid, in the middle at melting point, because it's heating curve, so it's melting point here, which is 0 Celsius, so this is for water. We have both of them, solid and liquid. At the end, after melting or above melting point, we should only have liquid. Easy, right? So let's go to this one. What if it's something like this? So this heating curve, look, it has two straight lines. What does that mean? So here we have two changes of state, meaning solid is changed into liquid, then liquid is changed into gas. So what will happen to it? Look, at the beginning you start with solid, it melts, right? So in the middle, in the straight line at melting point, so we have both of them, solid and liquid. Above this, we should only have liquid. Then at the straight line, this is boiling point, meaning liquid and gas, both of them exist. So at the end you should have gas. So look, you started with solid, in the middle solid and liquid, so you have liquid, in the middle liquid and gas, and at the end we have gas. Just do this and you'll know. Don't get confused. The only difference is here we have one straight line, so it's only from solid to liquid, okay? Here we have two straight lines, meaning it's solid to liquid, then to gas. And we have two numbers. The first one is melting point, the second one is boiling point. And this was it for this video and for this chapter. Inshallah, I will see you in the next one.